All right, welcome back, everyone. This example will be kind of taking the previous two examples up a notch, or maybe even up two notches. All right, we're going to worry with two blocks connected via an ideal string, and that string is laid over a frictionless, massless ideal pulley. Okay, so what I mean is, let's see, we have a ramp and a block. We'll call block one, and a pulley at the top of that ramp, and then a string is connecting the first block and some second block. Okay? And so these blocks are free to move, right? There is no friction on that surface, right? And block two is not touching, say, the inside of that ramp. Okay? So if I give you the masses, let's say mass 1 is 8 kilograms and mass 2 is 22 kilograms, right? Your instincts should tell you that mass 2 should accelerate down and mass 1 then will accelerate up the ramp, okay? I also should specify the angle. Let's say that is 30 degrees, okay? And so what we want to do in these typical problems is solve for the tension in the string and the rate of acceleration. Okay, so two things. If you can see ahead a little bit, you might see that there will actually be four total equations, right? Two second law equations for both objects, right? So we'll have components going every which way, so we'll need to be very careful, okay? But we'll follow the same exact process for the free body diagram as before, okay? So let's get to it, right? We want to solve for the tension and acceleration of both objects, okay? So to start, I said that the string is ideal, and that means that it's massless, it doesn't stretch, it doesn't compress, it doesn't twist, it doesn't do anything besides just connect two things. That also means that, well, the tension, say pulling the block one up that direction, has to be the same as the tension holding or pulling block two up that direction. Those tensions have to be the same. Okay? They have to be the same. Otherwise, if they weren't, that string would stretch. It would change its length as they moved. Okay? Because the tension stays the same, the rate of acceleration is also the same for both objects. You can effectively think of this block 1 string and block 2 system as one system. If that string does not compress or stretch or anything, they move in unison, right? So they have the same rate of acceleration. So let's draw a free body diagram. Let's leave myself some room. So let's do it off to the side here. So whoops. Here's our block 1, okay? And let's do 1 first. So we have a tension, right, up the incline. I'll draw that as T. We have the normal force perpendicular to that. And then we have gravity down, right? You can write it as FG. I know in the last video I wrote it as FG. I mostly will do MG. It's up to you, right? Write FG or MG. It's up to you. All right. That's all the forces for F1, right? Let's do F2 real quick. F2 is over here. 2. So let's see. The tension on force 2 is up. And the force of gravity is down. That's it. All right. So now that we have forces, we need, let's see, we need our axis, our coordinate axis, x and y. So if this block were to be released, if these blocks were to be released, mass 2 is much, much more massive. So they would go something like this. They would go up and down. So that means for block 1, the acceleration would kind of go like that, right? So let's do this. Let's draw x and y like that, right? So that leaves tension in the positive direction, okay? For block 2, positive is down. We have to keep that same sign convention, right? Or rather, we should keep that same sign convention. It'll be easiest if we do. So that means that I'm going to have one axis as downwards. And since we're used to, say, up and down as the y direction, I'll make that y, right? You can make it x if you want. It's actually arbitrary, but I'm making it y because that's just what we're used to, right? It's intuitive. And that means that the acceleration is also down. Okay. All right. Now it's time to break them up into components. So T and Fn are already in either x or y. They don't need to be broken up from mass 1. The force of gravity does have to, right? And so similar to last problem, we have components in the y direction and components in the x direction, like that. So in blue, that's mg sine theta, if our angle is right there, right? And it is because we specified that to be theta, right? That's the same as that, right? Going back to lab 1. There we go. Okay. And in red, I need to draw, this is mg cosine. All right. So let me take mg and put it over here. There we go. All right. Components for block 1 are down. Components for 2, do we need to break any up? No, I don't think so. Right? Gravity is straight down. Tension is straight up. There are no forces in the x direction. So we're good. And so now let's write out for mass 1, or we'll call it block 1. Doesn't matter. The net force in the x direction, well, that's tension, right? Tension is up the incline, as is our direction that we chose, or I chose, as positive x. So tension's positive. And now in the negative x direction, in other words, pulling down the incline, is the x component or sine component of gravity. So mg sine. All right. And that's all for the x direction. So that equals max. Right? In this problem, we know it will accelerate, and so it's not 0. It's max. That's the net force. Okay? All right. And the y direction is positive normal force, F sub n, and negative mg cosine. Right? That component is attracting the block or pulling the block perpendicularly into the incline. And that, yes, it is equal to may, but it's neither accelerating off the incline, right, up into the air, or into the incline. It's just staying there. And so, yes, that's 0. Okay. All right, for block 2, let's see, x direction, well, 0. There are no x forces. The y direction is positive down in our case, and so that is mg, and tension is up, so that's negative. And that equals positive ma y. There we go, right? Now, a quick word, right? I alluded to this in the previous video, but I don't believe I actually went back to it. Hypothetically, if I were to have chosen up as positive y, right? It still accelerates down, right? It still falls down, what we call quote unquote down, as in, well, that way, down, right? But if we say up is positive, that means that when we write our equation, the tension would be positive. That's the positive force. The gravity would be the negative one, but the net force would be negative ma, right? And so the fact that if you have your acceleration in the opposite direction to your positive axis, you will have a negative out front of your ma, right? So if you do that, do not forget that negative sign, right? It's essential. And that is why I always say, if you can help it, put one of your axes in the direction of A, right? That way you don't have to worry about possibly forgetting to write this negative sign. You just write it as MA. It's positive. Okay? So be mindful of that. If you can help it, always put one of your coordinate axes, right, in the direction of the object's acceleration. That way you can just write equals plus MA. All right. So in this problem, we're finding tension and acceleration. So can we find either of those straight away? We cannot, right? Tension is a factor of acceleration, both over there and over here. So we cannot solve straight away for it. Let's see. What can we do? Well, if we can realize that acceleration, right, the x acceleration for block 1 and the x and the y acceleration for block 2 are the same, we can take away those subscripts, right? They're both the same. What else can we do? Well, we have a system of 2 equations and 2 unknowns. Whoops. So what I suggest doing here is choosing one of the unknowns, solving an expression for it, and plugging that expression into the other equation. Right? So 2 equations and 2 unknowns. That means we have, let's see, this. mg minus tension equals ma. Uh-oh, I haven't been writing the subscripts. So this is m1, 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 1, and this is 2. All right, that's another thing. Don't forget subscripts, they're not the same mass. That's 1, 1, 2, 2. Excuse me. All right, so I'm going to solve this equation for t, and then plug that into the other equation and solve for a. So what I mean is that t equals m1a plus m1g sine theta, right? And so this is my expression right there. That's my expression. And I'm going to take that expression and plug it in for t in the other equation. Okay? So now we have m2g minus this whole expression, minus a. Distribute the negative, equals m2a. And now we have one unknown, right? Combine like terms, running out of room, m1g sine theta equals m2a plus M1A, and I'm going to try and do something really slick here. Let's see if I can do this. Copy. Moving to the next slide. Hey, it worked. All right. All right, still solving for A. I'm going to factor that out and divide by M2 plus M1. Okay? And because I don't like what I'm solving for to be on the right side, I don't know, it just makes me uncomfortable. I'm going to switch sides. There. All right. Just to make it explicit, this is what I did. Okay. And then I divided through. So we should know everything there, right? M2G minus M1G sine theta all over the total mass, right? So you can solve for the value for the acceleration from there, all right? So we should get a value of 5.89. At least that's what I got. I hope you get the same thing. If not, please let me know. Okay. And now that we know the value for the acceleration, we can take that value and plug it into either the equation there or this other equation right there and solve for t, right? I'm going to do it for block 2. So that means M2G minus T equals M2A, right? And so T equals M2G minus M2A. We know all of those values, and we should get 86.3 newtons. All right. So, like I've alluded to, or rather I've said it pretty plainly, the hardest part of these problems is being able to draw the free body diagrams and write the equations from them. Okay, this is the physics. This is the important part, right? This is 90% of the problem. If you can do this, right? If you can write out the free body diagrams from the original picture, oh man. Then if you can write out the equations based upon your axes, right? And the components that you've drawn, you're 90% of the way there. The other 10% is just algebra, right? Just this. This is the important part. This right here, okay? This stuff, the math, the final answers, not nearly as important as knowing how to do all of that, right? That's the important part, right? So again, try to recreate to get these answers, right? If you don't get these answers, please let me know. But I guess that's it, right? Thanks for watching.